Hello.
Hey, good morning.
Hi, I had a question.
Yep.
For the video reactions, I just typed a comment into the canvas.
Yeah.
Is that how we're supposed to turn it in?
That's fine.
Okay.
That's fine.
Okay. Thank you.
Either that way, or some people are just writing a little short thing and putting his email attachment, or just as an email. Either any way works, as long as I
Okay.
get it. Yeah. And
Okay.
you should get a response back where I say okay.
Okay.
I've read it.
I'll look for that.
Yeah, because I haven't looked at the ones from like last night or something like that. I'll be looking at them this morning.
Thank you.
Sure. Let me see if I can fish these up. Let's see. Okay, so let's get going. What I want to do is, I'll start out with sort of giving you a visual, because I'm going to be using Maui for a lot of this discussion today. I just did visually is easier, I think, for people to see. The other islands, stuff isn't quite so obvious. So Maui's sort of a real good sort of geologic, and especially when it comes to vegetation zones, it's a lot easier to see the different patterns you got. So I think last time, or maybe the time before, I was mentioning this whole idea of the fact that you have volcanic activity, subsequent or secondary volcanic activity, and this idea of rift zones. Again, if you think of the eruption last year in off of Pu'u vent, where you have that basically crack and then material coming out. That's very typical of the secondary phase of Hawaiian volcanic activity. Halakala, we'll get more into detail when I get into Maui later in the semester, but Halakala is probably one of the classic examples because it's so highly visible. It also sort of segues in this whole sort of, a process of change. So if we look at this overview here, we're now looking down at Halakala. Here's your central crater. So this is East Maui. Here's what, at least for technical purposes, we consider the East Crater. If you look over here, notice how you've got a line of cinder cones going all the way down here, a little secondary crack there going all the way down through Hana. This is a rift zone. At some point in the past, the side of Halakala cracked, literally cracked open. It was weaker and material started shooting out, not just in one spot, but in a whole mess of spots here, probably simultaneously. This is almost like firecrackers going off. So you can actually see the evidence of all these little volcanoes, very much like Diamond Head or something like that. Now the key when you're looking at all these guys, let's see if I can actually image. No, it's not show it. Is when you're looking at all these, you have to remember that this has nothing to do with the building of Halakala. The huge mountain that's this Halakala had been around for a really, really long time. This is all very, very recent. So it's actually not part of the building of this part of the island. It's part of a secondary system. The most spectacular and probably one of the largest, at least in that we have records, or well, not records of, but you can actually see it, would be here on the left-hand side. What happens is about, we're not really too sure when, but probably about maybe 50, 100,000 years ago, the west end of Halakala cracks. And what you can actually see is this enormous string of, very clear, almost like dashes and dots of volcanic eruptions that are going all the way down slope, continue all the way down to really large craters, and eventually continued pouring out. This last section here, which occurs from Pu'u here, that goes all the way down here. That fills up this whole area of La Perouse. This occurred in 1781. So this rift zone on Halakala is still weaker than the rest of the volcanoes, than the rest of the island, and it still is considered volcanically active. You can see another secondary eruption that occurred about 50 years earlier here from Pu'u vent, and basically filled this whole area here. We know from oral traditions that there were two Hawaiian villages, one here and one here, that disappeared, got swallowed up in the eruptions. And the oral traditions are very clear that at least in this one, the eruption happened so quickly that not everyone was able to get out in time. So it literally happened at night, and this stuff was moving about 40, 50 miles an hour. And by the time people realized what was going on, some people didn't make it. So active volcanic material isn't the prerogative of the Big Island. It's also found especially on Maui. So this is very, very fresh, very new material. But again, it has nothing to do with the building of this half of the island. It's part of a subsequent series. In fact, if you want to see it classically, you can see it right here. Here's the original crater. about maybe 150, 200,000 years ago, we're not really too sure, there was actually a crack inside. The whole center section weakened. And so material started pouring back up again. Now remember, the volcano itself was already built. So it had started to erode. Here you can see the older erosion patterns. This is the old erosion patterns here. But what happened is the material filled up and eventually melted, just like melting plastic, melted a hole in the wall of the volcano. And all the stuff just poured out just like a hot plastic or, you know, toothpaste or something like that, and poured down the coast. This is what's called the Kalpo Gap. And it's probably the best example I know of just visually. You can actually see there was a really deep caldera here, probably maybe 1,000 feet deep. And a very short period of time, it literally filled up with material. Material burned a hole or blew a hole in the wall of the side of the volcano, and just poured down here until it had drained out and cooled down. So Halakala is probably the best example of sort of the two phases. One is the initial island building formation, this huge shield volcano. And the second is the subsequent things that occur to that particular island, or that particular part of the island. So there's sort of two parts to this. One is the islands formed by volcanic activity. So huge amounts of material come up. You saw that in the video, and they form an island. The video also did not a bad job of pointing out then what subsequently happens is you have erosion. This is a combination of wind and water. And again, sort of atypical of most areas, because the vast majority of time we have our wind and our water coming this direction, blowing out of the north-northeast. And it does that for, you know, usually about 300 days of the year. So what happens is it's real uneven wear. So what originally was a, you know, fairly symmetrical round volcano, one side gets constantly hit by wind and water and it erodes it. Again, because the Hawaiian Islands are fairly new material and they're not particularly solid, it doesn't take a lot to cut this stuff away. So if you visualize this as actually being a nice little sort of round thing, you can see how the side here, the windward side, gets completely cut away. This originally would have been nice and symmetrical all the way out here to, you know, almost to Mokokui. But it's not now. This has all been eroded back. It's a little bit confused because you get the subsequent eruptions filling in spots. But you've got this huge cutaway. Most spectacularly, if you look at the older, you know, brother or sister of Halakala, this is the West Maui Mountains. Now, the West Maui volcano was basically the same size as Halakala, so it originally went all the way out here. And what happened is that I forgot, wait, hang on a second. Come on, babes. Oh, okay, I didn't know I was recording. At some point, what happened is that the West Maui Mountain went through the erosion phase. There doesn't appear to be a lot of subsequent activity. So unlike Halakala, when this part of the island was built, it pretty much stabilized. There wasn't a lot of secondary volcanic activity started refilling spots. So this is what Halakala will look like in about, I don't know, maybe 700, 650,000 years. All the soft material has been worn away by wind and water until all you've got left is the hard, heavy basalt that sort of is the basic, almost like skeleton, if you would. So this mountain, which is only about, I don't know, I think Pu'ukukui is about 4,000 or 5,000 feet high. This originally was 20,000 feet high. This was the size of Mauna Kea. But what's happened is since the time it was formed, this is all that's left. It's been worn down to a little nub of itself. But you can still see the basic shape. And if you notice again, notice how more cutaway this one, it was pretty symmetrical. This is completely worn away. It's cut away to the center. Here's the original caldera right here. And notice how there's, you know, this side is completely cut away to almost to sea level all the way in. The Lahaina side still has a fairly significant part of what's left of the old shield in place. So this is the power of wind and water, you know, wind and water 24/7, 365, hitting the islands but unevenly. This side's getting a large amount of water. This part of Iao Valley, the Iao Valley system, gets about 350 inches of rain a year. If you're in Olowalo Gorge, coming out of the gorge over here, you're at about, I think, about 40 inches of rain a year. And that's a distance of, I don't know, we've only walked back into here. We never made it all the way back in, but it takes a while to walk, but it's not a very long distance. In fact, people used to walk from what's now Wailuku, go through a trail and they could pop out in Lahaina and they could do it in one day. So you're talking very short distances and huge changes in the amount of water And not only that, the amount of wind. This area here doesn't get, you get 30, 40 mile an hour winds. In fact, Wailuku's, that's typical. You get over here and it's maybe still there 5 or 10 miles an hour. Why? Because these mountains blocked everything. So what happens is this is why the islands are shaped the way they are. And you can see it on Lanai also. If you notice, this side of the island that gets the rain and the wind is really cut away. This side of the island, which doesn't get the wind and the rain, is quite smooth. They're both eroded, but this area much, much less so than this side. And of course, if you go to us, again, you have to remember we're a much older version of what you see on Maui. In this case, here's the caldera, the crater for the east part of Oahu, the second half of the island, the Halakala, if you would. That's completely gone. And the actual caldera now is so eroded out that there's nothing left of this whole side of the volcanic system. All that you've got left is the skeleton of the western side, which is the Ko'olaus. So this is the western skeleton. But then in that, you can see on the leeward side, our side, the Kona side, you can still see little bits and pieces of the old volcano, which is entirely gone here. It's just been eroded flat. And this is all wind and water. And this is just persistent wind and water. And this is how the islands are formed, and this is how the islands are shaped. So, and again, the other thing is the video I think mentioned is that when you're going from here to here, through the island chain, you're going back in time. Oahu's, Maui, and I don't know, 500,000–600,000 years. I'm just guessing. I can never remember what it is. And the big Maui is what the big island will be in probably about the same amount of time. And by then there will be a new island forming off of here that will be the new version of the big island, especially most accurately be the new Mauna Kea is building right now. That's Loi'i. So that'll be the next of these. So they're sequential. They're very much like a conveyor belt, but they're a conveyor belt that works through time. So when you're looking at Maui is probably the best example of that part because it gives you an idea of the variation. Now, as you might visualize, and let's use West Maui because it's the easiest to see. If you've got all these and you got the winds constantly coming from here and the rain along with them, you've got this deep valley here, you've got this deep valley here. Now the mountains, the ridges here are going to actually catch the wind. You have to visualize if you ever go across the Pali, and you're going across the Pali from Kaneohe. So you're coming up from Kaneohe and you hit the Pali as you're coming up there, or even the other way if you're coming across the Pali from town. You notice that you've got this massive cliff there, the Napali. And what you also notice in the very early morning, what happened probably around 6 this morning, is you'll see clouds starting to form on the Napali as the winds blow across. Because you have to remember that basically that air, the trades that are hitting the islands like they're hitting us this morning, they're coming across from basically Alaska. They're moving over this open ocean for over 2,500, 3,000 miles. As the air is moving across the ocean, it's picking up moisture as the water evaporates. And it collects that because it's moving, because the moving air can handle more water. So it comes across and it gets increasingly humid. In other words, it's carrying more and more water. And it can keep on doing that for a long time until it hits something that stops it or slows it down. So when it hits this part of Halakala, for example, or the West Maui Mountains, what happens is this huge physical feature. The wind hits that and it stops it. So it sort of makes for like a traffic jam. What happens is the wind stops, it slows down, it starts to turbate. And in that process, it has too much moisture. So it starts to form clouds as the moisture condenses, and then it drops rain. So the mountain systems on the island act as basically as water catchment systems for moisture coming from the wind. So the wind brings in the moisture, the cloud, the mountains stop the wind drops the moisture. Now that the wind has dropped the moisture, the wind now is going to blow across here. Now that it's lighter, it doesn't have the moisture in, and it's going to blow across here. If you're over in this part of Halakala where I do my work, this area gets about 25 to 30 inches of rain a year. If you drive over to here, you're getting 200 inches of rain a year. What you do get here is you get a persistent wind because as the wind sweeps around, it hits Halakala, drops the moisture over here in Hana. Then it keeps on wrapping around the island, wraps around the volcano, and comes screaming down this way. So it's always very, very windy over here, but there's no water left in it. The island has stripped the water off, and you can see it right here. You can see right where it got stripped. The wind hit here, the moisture gets taken out of the wind, and the wind then continues minus the moisture. Now, one of the side effects of this is if you're poor old Kaho'olawe, you're in what we call the lee. So in the lee is actually a technical term used by sailors, which means that if you're over here, you're very frequently, this is almost dead calm. Why? You got winds blowing across here, it's windy here. Why would it be real not windy over here?
The island is blocking the wind.
Or the wind shadow.
Yeah, it's a wind shadow, wind, just like a wind shadow, rain shadow, exactly. It's blocking the wind. And that's what they call being in the lee, which is one reason why if you're in a sailing boat, you don't go through here, because you're gonna get stuck. If you're on, for example, even Hokulea, you go around Kaho'olawe, you don't go through the channel, because you're just gonna be, unless you got a motor, you're just gonna hang around there forever. So poor old Kaho'olawe.
I actually sailed with Hokulea, and when we went, we had to go all the way around Lanai and all the way around Kaho'olawe.
Yeah, exactly. And that's why, because otherwise it's going to be a real slow trip. Now, the other half of that is what happens to poor old Kaho'olawe then? Why does it look this dry and this sort of, to put it mildly, beat up? And I'll give you a hint, it has nothing to do with the Navy. The Navy shows up later, but it pretty much was not like the world's most attractive piece of real estate, even before that. What's the problem this poor island's stuck with? If you're a tree, why don't you want to live on Kaho'olawe?
Is the rainfall not good there?
Yeah, it's about 15 inches of rain because all the water got stripped off here. Remember, the winds are blowing this way. So the wind you have on Kaho'olawe is the wind that got all the water stripped out by Maui. Now, that has two effects. Because the wind now is very dry, what happens when dry wind hits water? We'll say that you have a dry wind blowing across here and you got a puddle of water on the pavement. What's going to very quickly happen to that puddle of water? See this in some place like Vegas. If you spill a glass of water on the cement in Vegas, it'll disappear really, really quickly. Why?
It'll evaporate because of the heat.
Yeah, the heat and the fact that you've got dry air will pick that moisture back up and put it back in the atmosphere. So poor old Kaho'olawe's got trapped by two things. One, it doesn't get any water because all the wind that's had the water taken out of it basically by the landform here, by Halakala. And on top of that, any wind that does come across here is dry. So any water the island would normally have gets sucked out of it. So it's like a double bad idea. Kaho'olawe is in exactly the worst possible place for an island to be relative to Maui. If it was over here, it'd be fine. If it was even over here between the gut and what's called the channel between the two parts, it would probably be okay. Where it is absolutely totally sucks. It's just like in the worst possible place. Now, Lanai gets a little bit of the same thing because, of course, West Maui strips a lot of the moisture coming off of here. So this part of Lanai is really, really dry. Now, ironically, the west part of Lanai is also very dry because if you notice, Molokai has done exactly the same thing. Here's the wear. Here's what's left. The volcano's center was here. So this is like Oahu. This is the southern, western lip of the volcano. But the winds coming across here hit this, the moisture gets stripped out. The winds come peeling over and they suck the moisture off here. Now, why is this area in the center a little more green? I'll give you a hint. It has to do with Lahaina roads. Visualize your wind coming down this way. Why does Lanai City get a lot more water than the guys down here or the guys up here? The winds are blowing this way. If the wind's coming across here, is there anything stopping it? West Maui Mountains are down here, Molokai's up here. Yeah, exactly. And that's why this section gets a fair amount of rain. The winds coming through here are holding their moisture till they hit Lanai. In fact, you can see the clouds right there. And so they drop the moisture here. But if you notice, you got this, you know, almost really incredibly striking. Notice how the moisture stops right here. This area is really seriously dry. And this west end, which is not too low, is seriously dry because that area has, basically the air has been stripped of its moisture. So the Hawaiian Islands are very predictable in that regard. And this is enormous amounts of water, because you have to remember this wind's been going for thousands of miles without anything slowing it down. This is one of the enormous differences we have versus, say, continental land, where between all the landforms and stuff, that's very unpredictable and changes a lot in terms of how much water and wind and stuff you've got. Here, it's like a, you know, it's like a robotized automatic thing. It just happens all the time. So that's your erosional patterns. Let me go back to this then. Okay. Now, the other half of that is because the winds are always blowing in exactly the same direction, there's no variation. You end up with another aspect of this, and the fact that you end up with these very, very complicated microenvironments. I think I mentioned that just a little bit when I was talking about environmental sort of endemic species. So what happens is each little tiny area, because of its position vis-a-vis the winds, the rainfall, what side of the island it's on, whatever orientation it has, even if it's just 5 degrees different than its neighbor, it's going to end up with very, very different environmental conditions. And different parts of different areas are going to end up with very different environmental conditions. We call these microenvironments. Now, you find them in a lot of areas, especially in desert regions. You'll find microenvironments. Think of like the stereotype of an oasis in a desert. That would be a microenvironment. But here in Hawaii, because we have so much consistency in the wind and the water, but you have the variation put in by, if you would, the bones of the volcanoes. I mean, with these very, very complex microenvironmental systems, and because the wind and the water are constant, these environmental systems are in place for a really, really long time. They have very little variation. So what you end up with is these very complex, very sophisticated microenvironments that are basically little biotic packages that are next to each other, but they can be pretty radically different, even though they're quite close. Manoa Valley and Palolo Valley, for example, have very different rainfalls and very different patterns of vegetation. And that's not surprising. You know, if you've ever lived in Manoa, you're constantly getting Manoa mist all the time. There's a lot of water that gets blown across from Kailua over the Pali into Manoa. So plants might not get a lot of heavy rainfall in the middle of the valley, but every morning they're generally getting mist coming in that gives them some water. We don't get that mist in Palolo. You get a little bit, but maybe I would use maybe 1/10 what you do in Manoa. Now, the two valleys are only separated by a narrow ridge, but they're very, very different environmentally. And that's very typical of the Hawaiian Islands. Almost any valley here in the Hawaiian Islands will be different than the valley next to it. And what that means is as plants and animals come here and colonize the islands, they very quickly become very specialized to the particular place they're in. So the plants and animals in Palolo over, hundreds of thousands of years would be different than the plants and animals in Manoa, simply because the conditions are slightly different, and to be most efficient in an environmental sense, in a selective sense, what you're going to do is you're going to try to be optimally set up for that particular scenario. So if you look at the birds, for example, and say the finches, you'll find that you have different finches in different parts of different mountains. And those finches all originally were one species, but over time they become very, very good at eating the nectar, for example, out of one particular type of flower, one particular type of ohia or something. So they become so good at it that they're hyper efficient. They're absolutely superb at that one thing. But in doing so, they've lost the ability to take advantage of other plants. So as long as that microenvironment remains intact and it isn't disturbed, they're happy campers, and they're probably at the sort of epitome of being a flying bird and eating nectar out of a particular plant. They're as good as it gets. They're the hyper specialized instrument. But of course, since they've made physiological changes, if something happens, if climate change comes in and that microenvironment changes, they're screwed because they've made physiological change. And physiological change takes a long time, a lot of generations to differ. To modify it is an incredibly risky process. By contrast, if you look at a lot of species like us, for example, but also the other primates and a lot of other animals, you find that what they do is they're not very optimally selected, but a lot of the changes they make are social. So they make changes in terms of behavior rather than having to depend on physiology to do it. And that means that they can adapt to conditions much more easily and much more quickly, and to a certain extent more efficiently than something that's more perfectly designed for a particular environment. It's like a very particular tool that does one thing really well, but it doesn't do anything at all for anything else. Versus a tool like a screwdriver, which can do a whole mess of things. It doesn't do any of them great, but you can use it for a hell of a lot of different things. Two very, very different ways of dealing with sort of environmental selection and such like that. In the Hawaiian Islands, the norm, due to the lack of predators and the stability of conditions, microenvironments and microbiotic systems were the norm, and in some cases still are. So what you find if you're in particular areas like, for example, the Maui wetland forest in Uplands Maui, all the plants and animals there are superbly designed to survive on that one part of Halakala. If you try to transplant, they've tried a couple of times to repopulate, for example, on Oahu, they die. If you try to put them somewhere else, they die. They're only working there. You can't go and move them somewhere else. They're absolutely superb in that one spot that covers maybe 2,000 acres in Maui. Outside of that, they just ain't happening. And that's very much the norm here. And because we're subtropical, the plants, and to a lesser extent the animals here, also are not the same as they would be found, for example, in the tropical Pacific. If you go to someplace like Tahiti, the plants and animals there's some specialization because there are some microenvironments. But most of those plants and animals are pretty durable, and you'll find the same plants and animals, for example, in Samoa or Fiji. Because there it's tropical and the variation in climate temperature isn't that great. So they're good at what they do, but they haven't had to hyper specialize. Here, because of the tremendously complex variations, hyper specialization was the way to be successful, because it meant that you were most efficient in that particular situation. So that's a really important aspect, because when you're talking about extinction here in the Hawaiian Islands, and of course we're always the poster child for one of the highest rates of extinction, at least that we have data for in the world. But that's, when you actually look at it from this context, it's not surprising. The minute that Polynesians landed here, a lot of these microenvironments were screwed. There was no way they could survive Polynesians, Polynesian pigs, the Polynesian rat, Polynesian dogs, the chicken, all the rest of that stuff. That change would just shatter a lot of these microenvironments, especially at lower elevation, because all of a sudden you're bringing large amounts of change. The change is not based on slow climatic change. It's based on really fast, very complex patterns of change occurring simultaneously, and these things can't handle it. We're never going to know, probably, unless you could go back in time, what the microenvironments were in the Hawaiian Islands prior to Polynesian arrival. But I can tell you, I can guarantee when you would walk through them, you wouldn't recognize almost any of that stuff now, because it's not the environment that was around here, say in 1700 or 1800 or something like that. Okay, let's get into technical stuff. In the Hawaiian Islands, you have, again, the constant is that the volcanoes are recent, the islands are very recent. Again, it's one of the mantras that I've already mentioned a couple of times. We're the most recent large pieces of real estate on the planet. And we're all from single volcanic events. So all of Halakala was originally built by one volcanic package of magma. It was pretty much built at one extended point in time. So it's a single geologic event. Now, for most of the planet, that's totally unheard of. It's invariably a complex pattern of multiple events, not here, because then that plate's moving off. And once Halakala is formed, then pretty much that's it. Now, then the center of new material moves further south, and it's Mauna Kea. So what that means, among other things, are not only on the rocks here, all pretty much exactly the same. They're all basaltic rocks from a particular chemical compound. But when they wear down and turn into sand and dirt, they are what we call lattisols. These are typical in tropical and subtropical environments. Most importantly, they're typical volcanic environments. Lattisols are very low in nutrition. Now, originally, when volcanic soil is still new, and you can do this if you go down to like City Mill and buy bag of you know, powdered lava. If you buy black rock or red rock, you can plant almost anything in it because it's highly nutritious, because it's absolutely, if you want to, fresh. Having said that, it wears out really quickly. There's not a lot of nutrition in it. It's just sort of new. So it's sort of like a real quick fix. If you actually have that stuff wear down and it turns into black sand or eventually turns into like red dirt, what you've got then is it's pretty much got no nutrition in it at all. Because if you're over here, let's go back to, doing it this way because I think that's one reason why I locked up last time. If you're over in here, we'll say that you're over near Haiku side and you're going to plant stuff there. All of the soils that you have here are the classic sort of what we call red dirt. They're basically high in iron content. They're basically hematite based. They're basalts. So they're the ground up, powdered up leftovers of the volcanic eruptions for this part of the island. Because they're on the windward side, they've been rained on constantly for hundreds of thousands of years, and all the nutrition is leached out of them. So for all intents and purposes, it's sort of like powdered concrete. They don't really have a lot of nutritional value in them, or what little value they have disappears pretty quickly. So in that context, what that means is these are what we call lattice soils. Because of their background, either volcanic, they tend to be acidic, or in some cases highly acidic. But the key thing about it is if you're going to try to plant something here, you decide you're going to put up some fields here. So you're going to plant dalo or something else, I don't know what, dryland dalo maybe. And you're going to plant in this particular location. The problem you're going to very quickly realize is you can get 1 or 2 crops in and they're fine. But after 10 or 15 years, this area, all of a sudden the plants are going to be exhausted. They're really tired. They don't have any nutrition. Basically, they're hungry. They're trying to grow, but there's nothing to help them to grow. And that's the problem that you have with lattice soils. You have to rotate things constantly. So you have to basically leave this area alone, let it rest. If you can, you put in something like sweet potato, it puts nutrition back in the soil. And then after maybe 10, 15, 20 years, you can go back and plant it again. So this land gets very tired easily. The soils get very tired easily. And these are what we call lattice soils. It's not as bad as you find in the tropical Polynesian area, where you have more rainfall and more consistency. Those soils are basically useless. If you're going to plant stuff there, you have to be very, very careful because it's very easy to what we call exhaust the soil, which just means you take the nutrition out of it. At that point, it's just basically powdered rock. Okay, so that's when you hear the term lattice soils, you hear it a lot when you're looking at environmental discussions about persistence and planting activities, especially, for example, you're trying to reintroduce native species somewhere, or if you're looking at exotics. One of the things about a lot of the exotics, especially, it's like, it's one of the paradoxes of, for example, Koahauli and in Keawe. Both of them actually do very well in lattice soils, and they actually put nutrients, especially nitrogen, back in the soil, which is one reason that Koahauli was imported here from Africa, was because the soils were exhausted. And so what you had is especially the early plantations were trying to figure out how can they re-fertilize the soils without spending money on fertilizer. And so that's why you find Koahauli being brought in. It's to take advantage of this and sort of fix the lattice soil situation. But this is a huge issue if you're talking about agriculture here in Hawaii, is what do you do with this? And of course, if you're a golf course, this is why they spend enormous amounts of money doing irrigation and constantly fertilizing the grass, because grasses on golf courses don't like acidic conditions, and they need a lot of food. So if you put in a golf course, you basically are coming up with something entirely artificial. And to keep it alive, to keep it, quote, green, unquote, you're basically having to completely fight against the actual soil conditions where you've got it planted, which is one reason why golf courses are incredibly polluting in terms of the amount of nutrients and sort of ex-fertilizers they wash out into the ocean and streams. It's because you're trying to put something in this type of a soil condition which is totally unsuited to it. So you're going to artificially make it work. But if you quit putting in fertilizers in the golf courses here, they'd all disappear in probably 5 weeks. The grasses would all die. There'd be nothing left but dust, and eventually, Koahauli and stuff would show back up. So, okay, with that, let's go into the regimes. And again, none of this is unique to the Hawaiian Islands. What is unique is the tremendous range that you see in such an incredibly short period of distance. Again, because of the height of the volcanoes, the fact that the volcanoes have a fairly even slope in many cases, means that you can actually stand in most spots in the Hawaiian Islands if you've got any visible range at all. And you can actually look over a couple of these environmental zones from one location. In most of the mainland United States or anywhere else in the world, you can see maybe one or two at most, but you're not going to see 3, 4, or 5. So what you find in some ways is the Hawaiian Islands are like a miniature version of what you'd find on a continental landmass, for example. But one might take maybe 500 or 1,000 miles to see the variation take place. Here in the Hawaiian Islands, you can get it within maybe 10 miles. And again, because of this, the combination of these patterns in very short distances, combined with the microenvironments, you end up with a stunning amount of environmental diversity, and it's sort of, land diversity in incredibly short distances, which is both one of our blessings and it can also, to a certain extent, be one of the nightmares too. So let's take a look at how some of these play out. The first one is what we call strand, and these are the technical terms we use for these different regimes. You find that, for example, in the Hawaiian context, which we'll get into either next time or next week, is that they were very, very sensitive and actually very clearly defined the difference between these. And again, that's because they were farmers. They had to survive on the resources that the land gave them. So they very quickly realized in a very astute way exactly what these zones were. And they had very different regulations in terms of what you did in these zones. And they pretty much split them up exactly the same way we do today. The modern system comes from a combination of geography and plant studies, dealing largely with European, conditions in the, from 1600s on. So they came up with these. They realized that when you're going through somewhere, you can see these different zones. And so that's where the terms come. They're in common use. You hear them all the time. The first of these is what we call strand. Strand vegetation is your coastal vegetation. And let's see if we can find an image here. The easiest way to try and find strand vegetation is go to one of the resorts. Oh, it doesn't work. So we're looking at strand vegetation. What you're actually looking at is the coastal vegetation that you see along shorelines. There we go here. Oh, here, so here's Onuli Beach near Makena. And what you see here is this would be the strand up to about this elevation zone. It's the zone of land that's impacted both by water and, most importantly, impacted by salt blowing off of the water. So anything that's going to survive in this zone has to be salt resistant. In fact, the most successful species would be a combination of the Niu or coconut, the hala or pandanus, and mangrove. Anyone know what those three have in common? Because if you wanted to, you could literally plant any of those here, where they're actually in the high tide zone. I'll give you a hint. It happens if you dig up their roots. How many of you know what a mangrove looks like? Anyone? Okay, maybe we ought to do that first. Let's see here. I'm trying to pull them. Okay, we got pictures. Okay. Okay, here's a mangrove, and this is in salt water. Okay. Salt kills plants. Okay. How can mangrove, coconut, and pandanus survive here in salt water? I'll give you, it has to do with their roots. What do their roots have to be able to do? Okay, plants need water. So the mangrove is going to get its water from where?
From the salt water.
Yeah, it's going to get it from the salt water. So what does it have to be able to do? You see the same situation?
Do they have to filter out the salt?
Yeah, it has to have some natural way to filter this out. In fact, if you use a filter on a boat, there's water filtration systems you can buy for boats. I don't have one on mine, but you can get them. What it's basically doing is mimicking what this plant does. What this plant does is it's actually over, how many millions of years, I don't know how it's figured it out, but somehow it's figured out how to make a membrane that the water can move through it, but the salt doesn't. So if you were actually to pull this out of the ground, if you pull it out of the water, you find that it's covered in what looks like green slime. But if you actually look at it more carefully, you realize that's actually green slime that's basically about 80% salt. The plant's sucking the water in that it needs to do this, but it's figured out a way to keep the salt on the outside. Now the coconut does exactly the same thing, and so does the hala, the pandanus. In fact, if you pull up a coconut plant, if you pull up the tree, you'll notice the roots have these knobbies on them, and they're actually very white. That white on the outside is the salt. So all three of these have come up with the same design. They have basically called a membrane that filters the salt out. And this is exactly what you have if you have a water filter, for example. If you go hiking, you've got a bottle with a water filter. That filter is doing exactly, that's a man-made version of this membrane, which is also why you have to change them all the time. What you find in things like mangroves and coconut and stuff is very cleverly, the plant actually is constantly building a new membrane and sloughing off the old one. So these guys can survive in conditions that nothing else can because they figured out a way to keep this from killing them. They get the advantages of the water, but they manage to design out the killing the toxic nature of the salt in the water. So this is what we call strand vegetation. And it pretty much defines your coastal zones. We didn't have mangrove till about, I think, 1840 was actually imported. And the coconut and the hala were actually brought in by the Polynesians. So prior to that, there's actually very little that would have existed on your strand zone because most of the endemic vegetation here is not particularly happy with strand conditions. Main one probably would have been, let's see, trying to figure out how to get out of here for a second. How come I can't? So the main one would have been, sorry, I'm distracting myself here. Would have been, oops. Okay. Would have been a few of the various coastal plants. You'll see just decorative ornaments like we got here on campus. But there's not a lot of the endemic vegetation that actually is happy in the type of conditions you're going to get in those type of coastal zones. So one of the side effects of all this is that, well, you can see it here with the naupaka, which is probably the main one of the Hawaiian, sort of stable coastal strand zone vegetations. Now, naupaka does it totally different. Naupaka can't exist in salt water. It has to be above the high water mark. But if you notice naupaka, that's the one we have outside here, which I'm sure you've seen all over the place. It has a real fat, heavy leaf that's almost got like a waxy hard surface to it. How is it handling the salt? It's not, I'll give you a hint, it's not filtering the salt. What's it doing instead?
Does it take it in and utilize it in a different way then?
Nope, it does the opposite.
Oh.
Think about it, you can either filter it so you can use part of something. What's the alternative? You see this, for example, with an N95 mask in COVID. Why do you wear the mask?
To keep it out.
Keep it completely out. So naupaka, with that very heavy leaf and with that glossy surface, the salt just sits on the outside. The surface protects the plant from the salt. And then every time it rains or water comes by, it washes the salt off, the plant's safe. So if you would, the surface of an alpaca leaf is sort of like its version of like an N95 or wearing a set of plastic gloves. You keep yourself separated from what it is you're afraid of or what it is will hurt you. So there's sort of two strategies. I try to work with it, which would be mangrove, hala, coconut. So you actually come up with some very sophisticated way to manipulate that to your advantage. Or like if you're an alpaca, you just basically say, screw this, I don't want to have anything to do with you, and I'm going to make a protection to keep you out of my life. So the two different ways that you're dealing with the same sort of environmental issue, that you're in that strand zone. So that's the strand area. So this is a very specialized area. Now, one of the other problems you tend to get into in a lot of the Hawaiian Islands is the strand zone tends to be fairly limited in actual what you might call fresh surface water. And this is why the coconut is so spectacular. This is why Polynesians, when they went off to new pieces of real estate, invariably would take sprouting coconuts with them and immediately plant them upon arrival. Because one of the huge advantages of coconuts, you see this, of course, with the recent popularity in coconut water, is that coconuts not only take water in and keep the salt out. Where do they store a lot of the water?
Inside of themselves?
Yeah, they store it in the nut. I've never liked the taste of what I call overripe or rotten coconut, which is the white meat one. But if you take a green coconut and you crack it, you get what you guys think of as coconut water, which is basically purified salt water in the case of a coconut. Now, one of the sort of weird side effects of this is if you have a highly polluted area, say, for example, downslope of a golf course, your coconut trees there and the fruit in them are much more liable to still have good, healthy, fresh water than almost anything else, because that filtration system is actually pretty effective for a lot of things, including heavy metals. So if you're a Polynesian and you find yourself in a place where you're not too sure about the water conditions, you limit yourself to the coconut till you can figure out what the hell's going on, because that's guaranteed purified, safe, fresh water source. So coconuts were never seen as decorative. The wood was, of course, incredibly useful for a whole mess of things. The fronds you use for making all sorts of stuff, including sails. But the core, the actual nut itself, was almost invariably consumed green. The thing you see of in stores now with the brown, what I would consider rotten coconuts with the white meat inside, that was too late. If it turns into white coconut milk, that was not what people consumed. They would use the white meat as a poultice because it's very effective and as a partial antibiotic on wounds. But you wouldn't, that's not when you used it. You used green coconuts. So this was one of your good examples of your strand vegetation. It's very, very limited because the defining conditions are the proximity of salt water. And so a lot of other species that otherwise might do okay can't handle this. And this is one reason why, if you think about it, if you walk in somewhere where you've got a strand vegetation, you walk back into a certain distance and then bang, everything changes. You've got an entirely different pattern of vegetation. That's the things that are just above what you might call the salt zone. They're in the area where salt brought on the wind doesn't get to, and salt water doesn't get to. And then you can have a much more complex, much diverse biotic system, because that's a lot of things that can't handle this are very happy in that next layer, which is basically your lowland zone. So strands are sort of interesting because you notice them they're most defined by the lack of variety. So if you go somewhere, for example, they say if you go to Kahana or someplace on this island, you'll notice in the nearshore conditions, you've got those species, and now will include ironwoods, which are also salt resistant, and things like your naupaka, and then there's not very much. You go inland little ways, and all of a sudden, bang, you got koa haole and all sorts of different things, exotics, endemics, whatever. But there's this enormous diversity that you literally, it's just like someone drew a line in the sand, and you're not going to find it on that side because that's salt. This is salt defined. That's your strand. Your next layer would be basically inland of the salt, and it occurs in basically what are called your lowland regions. That tends to be really poorly defined because we don't really have much, if any, left of the endemic system of the lowland areas. Polynesians have so completely settled this in all the islands that what we have is the Polynesian landscape in the lowlands. So if you were to go and try to figure out what if, for example, existed on the slopes of Leahi Diamond Head, the only thing you could figure out would be the vegetation that was there at the period the Hawaiians had settled that area. If you do palynology, if you go back and look at the pollen analysis, you can find some evidence for what might have been there in that lowland zone between the uplands and the strand. But you're going to find very little left of those species. Almost everything there is a Polynesian import. Of course, even those then get dominated out by the importation of various exotics, intentionally or unintentionally. So, for example, if you walk around Diamond Head, with the exception of a few Polynesian plants, i.e. Hawaiian plants that are there, you're not going to find anything that existed there prior to 1850. The grasses, the nasties, the ukus, everything that you see in there, from the nastiest little weed to the largest tree, all of that stuff is exotic and basically exotic, and has only existed in the Hawaiian Islands for about 150 years. So the lowland zones, from a biologic, but from a zoologist standpoint, the coastal lowlands are gone, and that trying to restore that would be, to be honest, sort of an effort and futility, because we're not even sure what it would look like. We don't know very much about, sort of a huge mystery. It's a big question mark, this area between these two. Lastly, let's go here. We'll stop here as our last one. Let me switch over here. Okay, next, I'll do this just to finish up because I got it so I don't forget. This is the next zone. This is what we call the dry uplands, or the scrub uplands. This was actually one of the largest pieces of real estate in the Hawaiian Islands. A large part of the Hawaiian Islands are based in what's called scrub or dryland forest scrub up zone. And this is a good example. This is my area of East Maui. This is the edge of Hawai'i. And what you see here is a combination of the two patterns. Almost everything you see vegetation-wise around the edges here. Here you got Koahaole or Halekoa, depending on which way to phrase it. The grasses here are almost all exotic. They were brought in the 19th century for pasture. So what you've got here is a whole messy, pretty ugly collection of Sodom and Gomorrah weeds, various types of weed grasses, your Koahaole. All this stuff is exotic. So none of this would have been here even 150 years ago. You've got some Milo up here, some Ohia up here, and here you've got the main player. This is Vili Vili. So what you've got in the middle of this new area is a remnant of what the Hawaiian landscape used to look like from about 500-foot elevation up to about 3,000-foot elevation on maybe about 2/3 of the islands. And it's radically different than what you see in this picture. I'm sort of going to leave you with the picture, because this will be the basis of what we start on next time, is what did this look like? How did it change? And for example, everything you see here, including the Vili Vili, which is actually an endemic plant native to this type of environment, gets manipulated by the Hawaiians, who basically turn this into an agricultural zone, manipulating the environmental relationships this plant had with the other things around it. So the Hawaiians note the symbiotic relationship of a bunch of these species, and actually then take advantage of it to turn this into an area where they can provide food for themselves. So it's a very sophisticated manipulation of landscape versus the Western thing, which would be bulldoze it out, plant what you want, and like get the hell out of town. It's a very Polynesian way of dealing with landscapes. You change them, you modify them, but you basically tweak and modify what's already there. You don't try to replace it with something new. Okay, so with that, I think we'll stop since we're about halfway through this stuff. Okay, let me close out that. Okay, so first, any questions or anything? Apparently not. It's Wednesday. This is not a lot of questions. Wednesdays aren't good question days sometimes. Okay, so we're all set for now.
Other than the readings, is there any assignments that we should be working on? The projects?
I want you to, I've got this from some folks. Go back, look at the newest thing I have, which is the more detailed version of the archive, or the archival, the project, and let me know what it is you want to work on. I'm building up a spreadsheet that'll actually put everyone in it, so I can figure out what we can actually task people to do. So you're not going to have a choice in whether you're going to do the archival parts. You have to. You do have a choice in terms of which one of those themes you want to look at. The other classes split pretty evenly between oral history. I think two folks were looking at geology. One to look at the geology theme. Some folks are doing the land use theme. So it was pretty evenly spread out, which is good because that's easier for me to figure out what to give you guys to do. But the sooner you get in what it is you want to do, the more chance that we'll be able to find something that you find interesting. If you just wait by the end of this week, I'm just going to stick people in things because we don't have the time to mess around. We need to get you guys up and going so, you can actually start working on it. All right. And most importantly, I'm going to have to actually teach you guys what it is I want you to do, I think. So yeah, that's going to start up pretty quick. So look over that stuff between now and tomorrow. And just figure out which of those looks the most interesting or the least boring. I don't know, whatever category one is.
Okay, sounds good.
Any other questions, confusions? We all good? Okay. Okay, in that case, I guess I'll see you guys. Take care, and I'll see you guys on, I hope it's Wednesday. Yeah. So I'll see you guys on Friday. Okay.